Good evening, welcome to my laboratory. That's that light bulb glowing brilliantly on the 12-volt battery, connected just straight through, and I have the oscilloscope probe looking at what the light bulb is seeing. And in the previous video I demonstrated that the capacitor doesn't pass DC, so we'll do that again. We'll just hook this to the capacitor and you'll see that sure enough the light bulb is out now, but if I hook it to the without the capacitor to the positive rail, then the light bulb comes on nice and bright. Okay, and I'm also going to be monitoring what the light bulb is seeing, the signal if you will, with oscilloscope. So here's, we need to pay attention now for this one because where the baselines are is very important. So the channel baselines are in the locations indicated very carefully, and now we'll turn it on, and we got to turn on. Okay, so there you saw the A channel jump up from there to there. That's the 12-volt battery that you're seeing right there. Now we're going to keep both channels on DC coupled for this whole experiment demonstration. Okay, so the A channel is seeing what the light bulb is seeing. The B channel of the oscilloscope is what the function generator is putting out, and we're triggering off of the external trigger input from the function generator to keep a good solid trigger. So we're seeing a sine wave from the F43 at 10 volts per division. Right now I've got it cranked up kind of high. I should probably turn it down. Okay, so let's look at a peak-to-peak swing of about 12 volts there. Alright, and that's at about 1.5 megahertz as in the previous demonstration. Okay, so the DC we know passes fine and lights the bulb, and does not pass the capacitor and does not light the bulb. And when we've hooked the capacitor to there, that channel's voltage now has dropped down, as it should, to this is the zero baseline level, right? Okay, so now let's get rid of the battery for a moment. Okay, and that's the black lead from the function generator, and that's the red lead from the function generator. So first we'll just go ahead and hook it up to the positive bus, just like we did the battery. Okay, boom. And that gives us a little bit of light, and that's because the function generator's output voltage is drawn down because of the load. So we'll crank it back up to where it's putting out a good decent 12 volts peak to peak, but or rather the peak value is 12 volts, but the RMS value is going to be much less than that. In fact, they give you a little dotted line on here so that you can see what the RMS value of a sine wave is. Isn't that cute? Okay. And we're looking at the load channel there on channel A, and we're looking at that right now at 10 volts per division. So you're seeing the voltage drop from that light bulb lighting up there, right? You see that sine wave. And we can probably amplify that a little bit there. Alright, completely with us so far. Okay, now, and there's the light from that bulb, and if I go to the capacitor side, you get about the same light, whether you're feeding it with the capacitor or straight on the DC bus, right? Okay, except that you get a lot better signal over here when you're on the capacitor side. Okay, So let's re-attenuate that there. Alright. Okay, so now what I'm going to do is I'm going to put the function generator and the battery in series, actually. So first, let me turn down the output of the function generator. I don't want to blow my light bulb out. Okay, now, so let's see, I'm going to put it in series. So the red lead of the function generator, actually this doesn't really matter, but the red lead of the function generator goes, I'm just going to clip it up here, to the battery positive. Alright. Black lead of the function generator stays on the ground bus. And then the red lead from the battery here, we're not using the black lead there, the red lead from the battery comes over and hooks to, well, first let's hook it to the main bus there, okay? So we've got the function generator's output, the black lead is here, the red lead goes to the battery negative, the battery positive goes, wrong wire. Battery positive comes down and hooks to the circuit bus right there like that. Okay, so now the battery and the function generator are in series. The light bulb is lighting, so, and the voltage, I'm going to turn the voltage up now to where we get a good, same light bulb as before. Okay, so now the bulb is seeing the series voltage, the voltage of the battery plus the voltage of the function generator. So I don't want to go too high on the function generator's amplitude because I don't want to blow out that little light bulb. Okay, let's keep that going well. Now the thing that I want you to notice is the position of this A trace. This is the trace that we're reading with the oscilloscope probes over here, right? Okay, so the A trace, you can see where the baseline is right down there, right? So what's happened is the raw function generator output that we see there has had the battery voltage added to it, so the whole thing shifts up by the amount of the battery voltage. We're looking at that at 10 volts per division, so it's shifted up just about one full division. The oscillations from the function generator are obviously passing through the battery because the light bulb is lit, right? We know the capacitor blocks the DC. The trace has come down because this capacitor is blocking the DC from the battery, and all we're seeing now is the function generator's oscillations. Let me turn that up a little bit. Okay, see? So the light bulb is lit, the battery and the function generator are in series. We're going through the capacitor, and all we're reading on the oscilloscope is just the function generator's oscillation voltages, the AC component of the signal that includes a 12 volt DC offset caused by this battery being in series with the whole thing. Okay? So the current, or rather actually the voltage that the light bulb sees, and therefore the current flowing through it, is the instantaneous sum at any given time of this battery voltage and the voltage that the function generator is putting out, and the power being dissipated in the bulb is coming from both sources, the battery and the function generator. Okay? Just like when this battery puts out power, the power is coming from all of the cells inside this battery, right? So the battery and the function generator are acting together as one big power supply with a fluctuating output voltage, and they both provide power to the bulb, okay, through the capacitor. The capacitor, though, this capacitor filters out the DC voltage, and since we're looking at the circuit behind the capacitor, the oscilloscope probe does not see the DC voltage from the battery. So the oscilloscope trace is right around the 0 level, just like it is for a normal AC setting, even though if I move the oscilloscope, or rather the battery connection to the ground, or rather to the normal bus, you can see, what do you see there? You see that the trace is shifted up because the battery voltage is added to the function generator output voltage. And sure enough, the light bulb is glowing brightly too, because the light bulb, more brightly, because the light bulb is experiencing now the DC sum, the DC voltage here plus the voltage from the function generator. Whereas if I move the probe to here, even though both power supplies are in series, the DC part is filtered out by the capacitor, and the light bulb and the oscilloscope only see the AC component. Okay? Now guess what? What I've just shown is exactly what the AC-DC coupling function of the oscilloscope performs inside the oscilloscope. All it does is it breaks the direct connection, DC coupling, and puts a capacitor in for AC coupling in series, just like I've done on the board here, to filter out the DC component of a signal that has a fluctuating AC component. That's what AC coupling means. That's how it's physically accomplished in the oscilloscope, and that's what it's used for. Okay? Thank you for watching.